Hello, going to do friction 2, and I think I can probably fit all the work and force diagrams in these spaces, so let's give it a go, see what happens. 5 kilogram block, that's mass, is pushed across a floor, no slope. That means when we make our force diagram, the axes, my dotted lines, are just going to be regular-like, by a 25 Newton force. So I'm going to imagine that it's being pushed to the right, because this is a right-handed world that we live in. So it's a force of push is 25 newtons. The coefficient of friction is 0.3. And I'm just going to write right under that, force of friction is equal to mu times normal force. That's how I find that. And then we want to find the acceleration of the block. Okay, so what else can we put in this diagram? It's a 5 kilogram block, so that force of gravity is going to be 50 newtons. It's not moving in the up-down direction, so the normal force is also going to be 50 newtons. Can indicate the equality of those in the diagram. Good idea. And my force of friction is equal to mu times the normal force, which is 15 newtons. So now I can write unbalanced force is equal to this push is winning and friction is losing. And then I can write here mass times acceleration. Mass times acceleration is equal to 25 minus 15. So 25 minus 15 is 10, divided by 5 is 2. Want to hear a joke? Physics joke for you. Why did the cat slide off the roof? Because its mu wasn't big enough. Get it? Because cats say mew, mew. And mu is the coefficient of friction. There you go. That's physics humor for you. All right, number 2. 2 kilogram block slides down a 20-degree ramp. Speaking of kitties sliding off things, you could have a 2 kilogram cat, kind of smallish, I guess. Let's see, 2 kilograms worth of block, so that would be 20 newtons of gravitational force. Now everything else in my diagram, including my vertical axis, everything's going to be now lined up this way. So let's see what we have. Well, maybe the first thing I should do is go ahead and break this, just like you're plotting a point, x, y, down to the end of that arrow. Hope you're getting a little bit more betterer at these. And obviously this skinny angle down here is the 20-degree angle. If you make your 20-degree angle look like 20, less than 45 that is, then that will help. So I'm going to make sure I'm in degree mode. I am. And then I'm going to do 20. It's my gravitational force times the sine of 20. And then I'm also going to do 20 times the cosine of 20. That'll give me the two parts. And if you bring them both up at the same time on your calculator, if you've got one of these calculators that will do that, you can see that's the short one, that's the long one, so it's pretty obvious where they go. Of course, you can do your opposite, adjacent, all that stuff. So that's the 6.8 newtons, and this is the 18.8 newtons. Okay, so what else do we have? This 18.8, the up and the down have to balance. This is the up, this is the down, so that means that the normal force is also 18.8 newtons. And the coefficient of friction is 0.15, and I know that the force of friction is equal to mu times normal force. Notice I'm always writing down the equation that I'm using before I start jamming numbers in. And the normal force we just found is 18.8. So I don't remember my 18.8 times tables. So I'll use a calculator for that. That's about 2.8 newtons. That's here. I'm going to make it look small. If this is 6.8, 2.8 is going to be smaller than that, so I'll try to make it look right as much as I can. Okay, so now unbalanced force is this minus this. So unbalanced force is equal to, this is the sine part of the gravitational force minus that force of friction. Unbalanced force is equal to mass times acceleration. The sine part of the gravitational force is 6.8 minus 2.8. So the look at that, it's 2 again. 6.8 minus 2.8 is 4 divided by 2. I guess the acceleration of everything is just 2, right? No, probably not. That's just a coincidence. Number 3, 10 kilogram box is pulled across a rough floor. Now this is a flat floor, so that means we just need regular axes like this. We only make slanted axes when we're on a ramp or something like that. Okay, so we want to find the acceleration of this box. Let's go ahead and see what we can do here. Force of gravity here is, there's the mass of it, times 10 is 100 newtons. The pull is this way. I don't know why I did it that way instead of going like that. I guess because I'm right-handed. So that's the force of the pull is 50 newtons, and that's 30 degrees. Now notice this is going off into one of my quadrants, so this is the thing that needs to get broken up, doing the sine and cosine. Let's go ahead and do that. So 50 sine 30 is going to be 25, and 50 cosine 30 is going to be 43. Yeah, 43.3. So if your picture's good, you know which one is which because there's a short one and a long one. Otherwise, opposite goes with sine, right? Sine is opposite over hypotenuse and all that. Okay, what is the normal force? This, I find that students struggle with this because at some point we have lots of examples of problems, like number 1 here, for example, where the gravitational force and the normal force are equal to each other. But that's not always the case. Like here, for example, once we get slanty here, the support force, or normal force, is equal to this, right? Because ups and downs have to balance. And then here, ups and downs have to balance. So in the up direction, I have this and this. So I find that most students who make a mistake here make the mistake of forgetting that this is also in the up direction, and ups have to balance downs. So this is not 100 newtons. This and this together have to equal 100 newtons. So if you want to write an equation and do some algebra, you can do that. You could write like force, the support force plus 25 newtons has to equal the force of gravity, and then do the math. Or you can look at it and be like, well, if 25 plus something equals 100, that's going to be 75, if you're confident, just kind of staring it down like that. But that is not 100. We also have friction, and I need to figure out how much. So the force of friction is equal to mu times the normal force. So mu is 0.25, the normal force is 75. That's going to be about 18.8. There's another 18.8. Go figure. So, okay. And then we're ready to do unbalanced force is, this is winning. That's the cosine part of the pull, right? And then friction is losing, because friction is a loser. Friction is always losing. 10 times acceleration, that's mass times acceleration, is equal to 43.3 minus 18.8. So 43.3 minus 18.8 divided by 10 is about 2.5. So it's close to 2. All right. Some physics students, time. Ooh, boy. All right. Think about that. A 1 kilogram block sliding down a 30-degree ramp, and determine that it takes the block 0.71 seconds to slide 1 meter. Okay, now we get a time here, so what does that make you think of? I think when we have times and velocities involved in these problems where we're thinking about force diagrams, that is probably telling us that we need to do some kinematics. So that means this. Of course, come test time, you can have all these equations there. You just need to know when to use them, right? So I got time is 0.71 seconds. It goes that far, and that's a delta x. And it starts, they're releasing it from rest. That's kind of implied here, determine that it takes the block that long to slide down. So you got to read that into the problem. Those are the 3 things that we know. So we should be able to find acceleration now. That looks like the equation, this one. And my initial velocity is 0, so that term's going to go away. So delta x is equal to 1/2 a t squared. So we'll do a little bit of algebra here. So the acceleration would be multiplied by the 2, right, to get rid of that fraction, then divide by 0.71 squared. That's about, let's say 3.97. Actually, if we're just going to round to it, we could call that 4.0. That'll work. 2 sig figs is good enough for us. Okay, so I know the acceleration now. That's what all that was about. Oh, find the acceleration of the block. Check, did that. And then the coefficient of friction. And this right here says this is a little harder than the problems that you can expect to see on the test. And seeing as I'm the person that made this sheet and I'm going to be the person who makes the test, I would agree with that. So, like having to do all this kinematic stuff just to get the acceleration. Okay, now we got it sliding down. Now I'm going to make my force diagram. This is my 30-degree ramp. This block has a mass of 1 kilogram, so the gravitational force on it is going to be 10 newtons. Everything else in the diagram is going to line up with this XY system. First thing I'm going to do is break that up into the sine and cosine parts. So I got, what am I breaking up? I'm breaking up 10. So 10 times the sine of 30 is going to be 5. 10 times the cosine 30 is 8.7 or something. Yep. that. I've done this before. So this is 5 newtons here. This is going to be 8.7 newtons there. The support force, this block is not moving in this direction, so those up-down must be balanced. So the normal force is 8.7 newtons. And then I need to figure out how much friction. So what would the unbalanced force equation look like? Well, I've got this sine part of gravity minus the force of friction. But the unbalanced force, that's mass times acceleration, and I know the acceleration in this one. And the force of the sine component of the force of gravity is 5. Sorry, I was going to write newtons there, but I don't want to put the units in this equation because it'll make it messy. Of course, I made it messier by scribbling there. So that's this minus the force of friction. So that's 4 equals 5 minus something, so that's going to be 1 newton is the force of friction. And then this problem says find the coefficient of friction. So what's the equation that has the coefficient of friction in it? I know that friction force is equal to the coefficient times the normal force. So the friction force is equal to the coefficient times the normal force. And that means call it 0.11. So yeah, there's a lot going on in that one. All right, number 5. A 2 kilogram block is attached to a 100 gram hanger. I'm just going to right off the bat here, this 100 gram hanger, that is 0.1 kilograms. Grams, no good. By a string over a pulley, if there's no friction, find the acceleration of the block and the tension in the string. Okay, so we're doing one without any friction here. So there's 2 ways to do this. Remember, there's the set up equations for both of them and then add those equations together, or there's use the totals, the total unbalanced force, total mass, to find the acceleration. So either way, if we're going to find the tension, we're going to have to think about either one or the other of these things to get at what that tension force is. And for sure, I need to make force diagrams. So let's do that. For the block up here, I've got the force of gravity. That's 2 kilograms, so that's going to be 20 newtons. Not sure how much tension there is. And then for this hanging one, force of gravity on that is going to be its mass in kilograms times 10. So that's 1 newton. And then the force of tension is definitely less than that because I know that it's going to accelerate down. So this must be winning. Okay, so if you wanted to use the, I think of this as being like the shorter method. So what's the total unbalanced force? Well, the tension forces cancel each other out if we're looking at the total, right? That's equal to that, that's equal to that. So all that stuff cancels, and this is the only unbalanced force. So that's force of gravity on the hanging block is equal to the total mass times the acceleration. So that's 1 newton is equal to the total mass is 2 plus 0.1 times acceleration. So 0.48, we'll call that. And then we want to also find the tension in the string. Now you can use either one of these. This one's kind of easy because the unbalanced force on this is just the force of tension. So for the, not the hanger, but the block, it would be true. If I do an unbalanced force equation for the block, it's just that force of tension. So mass times acceleration, which we know now, 0.48, must be equal to the force of tension. So the force of tension is going to be 0.96. Right. I don't think you would want to round that to 1 because then it would actually be equal to this, and then that would not be accelerating. And we know that that's not true. So there you go for that one. Number 6, an Atwood's machine is set up with a mass of 1.5 on one side, 1.2 on the other side. Find the acceleration and the tension in the string. So if there's no picture, it just says Atwood's machine. Like the full-on Atwood's machine is like this kind, where you got one mass on one side, one on the other. And if this is the 1.5 kilogram mass here, then that's going to accelerate down, and the lighter one will accelerate up. So let's make force diagrams for them. Here's the 1.2 kilogram mass, here's the 1.5 kilogram mass. So for this one's going up, so that force of tension is going to be winning versus gravity. And 1.2 times 10 is 12. And then for the heavier one, the force of gravity is going to be winning. Those are equal to each other because it's the same string. Okay, so I'm going to use the same method of totals like I did here. Unbalanced force total is equal to mass total times acceleration. Unbalanced force total. Well, let's see. These cancel each other out, right? Those are equal to each other. If you're thinking to each other, wait, but if you're thinking to yourself, these are both up. How could they cancel? Well, the pulley kind of is redirecting things. So this is really like two different directions on that string. So those they're equal to each other. They cancel out because it's a string. Just like this, which is sideways, canceled with this, which is up. The pulley allows for that kind of redirect, and that's part of what we expect with an Atwood's machine. So what is the total unbalanced force? Well, it's the force of gravity on the big one, let's say big block, minus the force of gravity on the little block. That's equal to mass total times acceleration. If you're thinking to yourself, yeah, I see what you're doing there, but I wouldn't have written down this extra equation here. I guess that's okay. You could go straight to this. I just like to have that unbalanced force expression where it shows the winner minus loser kind of situation. The total mass here is going to be 2.7, right? 1.2 plus 1.5. And make sure you keep your forces and your masses straight. So it looks like the acceleration is going to be 1 and change. And I'm going to find the tension also. I think I don't really have enough room to do that, so I'm just going to borrow the back of our first page here. Which one of these equations should I use to find, or which one of these diagrams should I use to then make an equation and then find the tension? Either one, it doesn't matter. I'll do both so you can see that we get the same thing. So here, for this one, tension is winning. So unbalanced force is mass times acceleration. This is for the 1.2 kilogram block. Unbalanced force here, tension is winning. So force of tension would be minus force of gravity is equal to mass times acceleration. So 1.2 times 1.1, and then I'll have to add the 12 over. 1.2 times 1.1, and add the 12. So about 13.3. And that makes sense. It's supposed to be winning, right? It's supposed to be beating that. Okay, how about the unbalanced force on the bigger block? Unbalanced force here, this one's accelerating down, so gravity's winning. Force of gravity is 15 minus, I know the force of tension is 13.3, but I'm trying to do it again just to show you that you could have used either one of these. So I'm going to pretend I don't know what it is still. The mass of this block is 1.5 times the acceleration. So here, algebra-wise, I would have to add the force of tension over here and then subtract this. It's 15 minus that. 15 minus 1.5 times 1.1. Hey, 13.3. If you're like, no, that's 13.4, that's wrong. Well, we rounded things along the way. Remember, this was really 1.1 repeating. So let's settle down, all right? So we're going to call it 13.3. All right. There's my tension force for number 6. And the last one, number 7. Two 1 kilogram blocks are attached by a string over a pulley. One block is on a 20-degree ramp and the other is hanging freely from the pulley. The coefficient of friction is that. Find the acceleration of the blocks. I think this would, I would call this one also harder than test problems. It's not that bad, but let's see what we can do. So here's my 20-degree ramp, and we got a pulley at the top of that, and both of the masses are 1 kilogram. One here. If you couldn't figure out, it would have been nicer for me. I didn't have a diagram ready to go for this, so if you didn't really understand what this was describing and you're looking at this, you're like, oh, okay, I get it. Then pause this and, give it a shot. Okay, so whatever we need to do here, definitely we need to make force diagrams for both of these. And one of them is on a ramp. Force of gravity on each one is going to be 10 newtons. And I'm going to go ahead and break that up into the components by doing 10 sine 20, 10 cosine 20. So 9.4 and 3.4. Okay. Everything else I draw in this picture is going to be lined up like this. So the support force is 9.4, and the tension is I don't know what. But when we draw the other block, you're really making a guess. One of the things that's tricky about this problem, or did I tell you? I should have probably told you this. It'd make it like a tiny bit easier, but Or maybe you just intuitively think, when I let these things go, this is going to accelerate down and this is going to accelerate up the ramp. You would be correct if you assumed that. But it is possible, depending on this angle and other things about this, that it, or like if this is a heavier block, that could go down and pull this thing up. But not in this case. Okay, so that's 10 newtons, and then that's winning versus the force of tension, which is I don't know what. But those are equal to each other. Now, there's also friction here, right? There's coefficient of friction. So where's the friction and what direction is it pointing on? Well, it's not on this block, because this is just hanging. It's on this one, and friction always opposes the direction of motion. So friction is actually another force here. It's like a second one in here. And I'll just draw a little arrow pointing to it because I don't have space for a label in there. So there's also a force of friction here. That makes this problem tricky, I think. So if we wanted to do the same method where we look at the totals, we can do that here. The total unbalanced force going to equal the total mass times acceleration. And just to remind you, how come we don't say total acceleration? Because these two things are attached by a string, so they're going to have the same acceleration. There's no like total acceleration, it's just the acceleration. Okay, so unbalanced force total. This, the force of tension cancels out inside of our totals. This and this are equal to each other. The force of gravity here, that's winning. Force of gravity on the hanging block minus the sine component of gravity on the hanging block, right? That's that 3.4. Minus also is losing, is that force of friction, right? So this is winning and these two are losing. That's what I'm trying to do here. And that's got to be equal to the total mass times the acceleration. Okay. So let's see. I'm going to write off to the side here. I think I have just enough room to do my force of friction is equal to mu times normal force. So the force of friction here is equal to mu times the normal force, which is 9.4. 2. Oh, I think I'm going to call it 2.4 because I'm rounding everything else to the nearest tenth. If you make different rounding decisions than me, you might get a slightly different answer, and that is just fine. Okay, so let's see what we can do here. Force of gravity on the hanging mass is 10. The force of gravity, the sine component of that, that's my 3.4. And then I just found the coefficient of friction is 2.4. And that's equal to the total mass, which is 2, times acceleration. All right, so it looks like we got our acceleration. So I have 10 minus 5.8 is 4.2 divided by 2 is 2.1. I think I did that math right. That's 5.8, 4. Yeah, I think that looks good. Okay, and then last part is just to find the tension in the string. I think clearly this is going to be easier to work with than this, but just like we did in the last problem, you could use either one. Should get the same answer. So doing an unbalanced force equals mass times acceleration. This is for the hanging one. Unbalanced force here is gravity minus tension, winner minus loser, and force of gravity there is 10, force of tension is what I'm looking for, mass of that block is 1, acceleration is 2.1, so add this, subtract that, looks like my force of tension is going to be 7.9 newtons. That's how you do physics.